This is CPE 133. We are in Free Range Verilog Foundation Modeling Chapter 16. We are talking about verification, namely test benches. This is Part B, second lecture in the series in this chapter, and let's go. Disclaimer. You got to do this to learn it. Crank out some designs, make them work, ask good questions. Very doable. So a quick overview of what we've been doing. Digital design is a two-part process. It's design and verification. Verification, essentially there's two different worlds there. Design, you are making sure that your codes, your Verilog code or your Verilog model synthesize, where verification, you're not going to synthesize it. So it's a completely different requirement, completely different mindset. Certainly verification is the harder part, particularly for complex circuits. The idea is you have to understand the circuit and then have to know how to test it in such a way that it's actually testable and you have a good feeling that it's actually going to work. So our approach in CPE 133 is very limited. We're just doing one type of simulation, which is essentially behavioral simulation as opposed to functional simulation, and we are just generating a timing diagram and staring at those. By all means, if you want to do more, go for it, but that's pretty much all we have time to do in this course. So this is our general model of our test benches. We have the design we're testing, and then we have the stimulus driver, which is Verilog model, and the stimulus driver is going to be sending inputs to the design. The results of those inputs are going to be the outputs, which we can look at in a timing diagram, or we can actually send those outputs back to the stimulus driver and have the stimulus driver do something intelligent with them. Pretty much in this course, we will be sending everything to we'll be looking at the outputs in a timing diagram. So what we didn't do in the last set of lectures is generate a clock signal. So typically there's going to be a need to generate some type of periodic signal using Verilog, and it's really nicely done. Verilog has some looping constructs, and particularly these looping constructs are very handy when you do some complex testing. Now these looping constructs are very much like higher level languages, but the one loop we are interested in here is this forever loop. Essentially, as the name implies, once it executes forever, or at least for us, it executes until the simulation ends. Very simple syntax here. We'll see some examples in a second. So this is our example problem. We'll do one example here. It's essentially what we're going to do is test an n-bit counter. So this is what we want to do is grab that counter, make it an 8-bit counter. I guess it calls out for an 8-bit counter. It essentially means we're not going to override this nice parameter right here. But this is a model we've used before. It's actually, looking at this, it's an up-down counter, and it's loadable, and it has an asynchronous clear, all good stuff. It also has an RCO on the output. We've seen those. You can see that the RCO is dependent upon the count direction also. This is stuff we covered in a previous chapter. So the issue here is we want to look at how to generate that clock signal. So before we did stuff like this in our previous test benches, which essentially just assigns all these values, blah, 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 and weights, and assign values and weights, etc., etc. And which works fine. But what else we need to do here is generate that clock signal. And so we can see it right here. We are going to use a different stimulus driver especially for the clock. And so we go back to this, and we can see that here are my two initial blocks, and there is the initial block that generates the periodic signal. So what's kind of neat about this is that I start that clock off at 0 just to give it an initial value before I start, because the very first thing I do here is delay. Now if you don't do that, it sometimes messes up the simulation. This is kind of a cookbook statement here. There's actually many ways to generate a periodic signal. This is the one I like using. So here's your forever loop right here, and what it's saying is it waits 10 time units and then it toggles the clock signal. So it takes the old clock signal, toggles it, and makes that the new clock signal. So this is going to be provide your periodic clock signal, etc., etc. And then I have this other process here, this other initial block that is going to be assigning the other output. So the cool thing about this is I can have as many initial blocks as I need to in my design. They run quite nicely together in parallel, and so no need to worry about that. The issue here is if you use them separately. I mean, this is a case where we pretty much had to do it separately, just because it made the periodic signal generator doable. But by all means, you could actually have initial blocks for any set of signals you want, just to make your test bench simulation more readable. And so that's it. Only other comment here is it does use this horizontal instantiation, which you don't want to do. The clock, everything assigned from those initial blocks is going to be, since it is a procedural statement, they need to be declared as reges. And lastly here, what else is interesting in here? There is no $ finish in this, which means that I'm relying on the simulator to finish for me, and I think that's all I can think of. So in summary of test benches here, test benches are the Verilog or the HDL way of just saying that, hey, this particular Verilog model is used to verify the proper operation of our circuit. So there's two types of verification approaches. One is is essentially a behavioral approach, which just tests like the logic in your circuit, and the other one's some type of functional verification, which actually is more closer to real life testing. Now, Verilog has a whole bunch of different supports for verification. We touch on just a few of them in this chapter. The language itself, and particular System Verilog, has a ton of more in there. I'd encourage you to go look at those. So the two parts of a test bench are the stimulus driver and the design under tests. And the stimulus driver is essentially a Verilog model full of stuff that's not necessarily synthesizable. So we learned about the initial blocks in this chapter, which is a procedural block that executes once at time 0 in your simulation. Some similarities with an always block, but a little bit different in general.